Let me take you back to 1999. I'm in a basement laboratory in Cambridge, Massachusetts, with a piece of equipment I named the candlestick. It's not poetic, it's functional. It works the way a candle wick draws melted wax upward, except instead of wax, it's sodium atoms lifted from molten metal, and instead of heat, it's laser beams. Those atoms travel up into a magnetic trap where I cool them using photons fired from every direction. Each photon that hits an atom delivers a tiny kick of momentum, slowing it down. Cool them enough and the temperature drops. We needed to drop it to 50 billionths of a degree above absolute zero. That is not a temperature that exists anywhere naturally in the observable universe. The cosmic microwave background, the coldest thing most of us can imagine, sits at 2.7 Kelvin. What we were creating was 50 million times colder than that. We were making the coldest matter on Earth, possibly the coldest matter anywhere, using lasers and magnetic coils and a household-inspired apparatus in a basement. When those sodium atoms reached that impossible temperature, something happened that I had spent years preparing for and still wasn't ready to see in the data. The atoms stopped being separate particles. Their quantum wave functions overlapped completely, and when quantum wave functions overlap completely, you no longer have distinct particles. You have one wave function describing millions of atoms simultaneously. That's a Bose-Einstein condensate. Albert Einstein predicted this mathematically in 1924. We didn't make one in a laboratory until 1994. The gap wasn't theoretical. The gap was that nobody had built the apparatus. I built that apparatus. In 1999, I sent light into it. Not ordinary light. I used something called electromagnetically induced transparency. I fired two laser beams simultaneously. The first laser, the coupling beam, I tuned to a specific atomic transition. It prepared the atoms in a quantum superposition, partly in one energy state, partly in another. That superposition made the atoms invisible to the second laser. Normally, sodium is opaque to the wavelengths I was using. Shine a probe laser at sodium atoms and they absorb it immediately. You get nothing. But with that coupling laser establishing the superposition, the probe laser passed straight through. The condensate became transparent. Here's what's elegant. That transparency comes with a cost. The quantum interference that prevents absorption also dramatically reduces the speed at which light travels through the medium. The condensate wasn't just transparent. It was transparent in a way that makes light creep. We measured a group velocity of 17 meters per second. The fastest thing in the universe was moving slower than a bicycle inside my cloud of atoms. I checked that number 3 times before I believed it. 3 times. We published it in Nature on February 18, 1999. Now let me connect this back to that piece of glass in front of you, because the same fundamental process is happening in both places. Glass slows light to about 2/3 of its vacuum speed, because light hits silicon atoms at room temperature, gets absorbed, triggers a quantum interaction, gets re-emitted, hits the next atom, and the process repeats. In my condensate, the process was identical. Every atom was in the same quantum state. Every atom was responding in perfect unison. The carefully engineered interference of the coupling and probe beams pushed the effective slowing to a factor of roughly 20 million. Glass slows light by 1.5 times. My condensate slowed it by 20 million times. Same mechanism. Unimaginably different scale. But here's the crucial part. In both cases, the information in the light was preserved. The photons exiting the glass weren't the photons that entered, but they carried the exact same encoded information. In my condensate, the same was true, except the information was moving so slowly and the medium was so perfectly controlled that something extraordinary became possible. We could stop the process midway. In 2001, I sent a light pulse into the condensate and let it begin slowing. Then I switched off the coupling laser. What happened is one of the most counterintuitive results in modern physics. The probe pulse didn't escape, it didn't scatter, it didn't disappear. It was converted entirely, coherently, without any loss of information, into an imprint in the quantum state of the condensate. The atoms reorganized their internal quantum states to encode the complete pattern of the light pulse. The light became matter. I held it there, frozen, for a fraction of a second, a period long enough to control, long enough to read, long enough to be a memory. The information that had been traveling as light was now stored in the quantum correlations between millions of atoms. Then I switched the coupling laser back on, and the light came back. Not a copy, not an approximation. The exact same pulse reconstituted from the atomic quantum state exactly as it had been stored. Light stopped. Not slowed. Not dimmed. Stopped. held inside a cloud of atoms waiting to be released. I need to be precise about what stopped because physicists sometimes get confused here. The individual photons didn't freeze. Photons always travel at the speed of light. That's what they are. What stopped was the pulse envelope, the group of photons acting together as a signal. The information stopped. And information is what matters. In quantum communication, what we need to store, transmit, and verify is information. A qubit, a unit of quantum data. In 2001, we stored that information in matter. We wrote it in atoms and read it back out as light. This is a quantum memory, not metaphorically, literally. A functional, peer-reviewed quantum memory. The condensate is the hard drive. The coupling laser is the read-write head. The stored information is a photon's quantum state preserved intact in the positions and internal states of millions of sodium atoms. In 2007, we went further. We used two separate condensates. We stopped a light pulse in the first condensate, converting it into a matter wave, a physical propagating disturbance in the atomic quantum state. We let that matter wave travel physically across space, not as light, as matter. Then we let it enter the second condensate, where it was reconverted back into light. A qubit, a unit of quantum information, was transferred from a photon to a matter wave to a photon, again across a physical gap, completely intact. Think about what that means. The information was a photon, then it was a wave of atoms, then it was a photon again. At no point was the information lost. At no point was a copy made. The quantum state, which cannot even be copied without destroying the original, due to the quantum no-cloning theorem, survived the conversion, the physical travel, and the reconversion. That 2007 result is foundational for quantum repeaters. Here's the problem with quantum communication that nobody talks about in popular science. You cannot amplify a quantum signal. Classical internet signals get boosted by repeaters. They arrive at a station, get read, get retransmitted at full strength. You can do this indefinitely. With quantum signals you cannot. Reading the signal collapses its quantum state. You cannot copy it. The signal degrades with distance in a way classical signals do not. The maximum range of direct quantum communication over fiber is roughly a few hundred kilometers before the signal becomes unusable. The solution is quantum repeaters. Stations along the line that store the quantum state, wait for both ends of the channel to be ready, and then teleport the information forward without reading it in a way that would collapse its state. For quantum repeaters to work, you need a quantum memory, a place where a qubit can be stored in matter, held, and then released as light. My condensate experiments are the direct experimental ancestor of that technology, not the inspiration, the proof of principle. Let's come back to the glass. Back to the question that started all of this. When light enters glass and slows down, it is doing in a primitive, room temperature, thermally noisy way exactly what light in my condensate does in a controlled, quantum coherent, ultra-cold way. It's negotiating with matter. It's being partially absorbed, partially stored in the quantum state of atoms, and then released and passed to the next atom. The light exiting the glass isn't the same photons, but the information is intact. The glass doesn't destroy information. It borrows the light's progress, delays it, and returns it. The reason light snaps back to full speed the moment it exits the glass is the same reason it travels at 17 meters per second inside my condensate. It's always traveling at the correct speed for the medium it's in. In vacuum, there is no medium. The photon has nothing to negotiate with. It moves at 299,792 kilometers per second because that's what photons do when there's nothing to interact with. In glass, it negotiates with silica atoms at room temperature and comes out at 2/3 of that speed. In my condensate, it negotiates with sodium atoms at 50 billionths of a degree above absolute zero in a carefully engineered quantum interference and comes out at 17 meters per second. The moment it exits into vacuum, back to 299,792 kilometers per second. The photon never forgot its speed. The photon always travels at the correct speed for its medium. The speed changes because the medium changes. The information does not change. It cannot change. The quantum state of the photon, its polarization, its phase, the qubit it carries, is preserved through every interaction in glass, in water, and in a Bose-Einstein condensate as long as the interactions are coherent. Here's something I don't normally say in print because it's speculative, but I think the evidence supports it, and you deserve the full picture. The light reaching your eyes from this screen right now has passed through glass, through air, through camera lenses, through optical fiber, through more glass, through the liquid crystal layer of the display itself. At every interface, it's slowed down. At every interface, it was absorbed, quantum mechanically processed, and re-emitted. The photons hitting your retina are not the photons that left the light source. They're the 1000th generation re-emission of a cascade of light-matter interactions stretching back to an LED or a laser diode somewhere in your device's backlight. And yet the information they carry is the same. The image is intact, the color is intact, the encoded data, the video frame, the compressed pixel values survived every single one of those interactions. Every medium light has ever passed through has been doing imperfectly and thermally and noisily what my condensate does precisely and quantumly and deliberately. Every piece of glass you've ever looked through was a low-grade quantum memory that held the information for a nanosecond and gave it back. The universe has always been trying to do what I made it do in 1999. I just found the conditions under which it could do it perfectly. Here's the question that opens everything and that I want you to carry with you. If the information in a photon can survive conversion into matter, if a qubit can travel as an atom wave and be reconverted back into light without loss, then the boundary between light and matter, between message and medium, is not as sharp as physics once assumed. What else can cross that boundary? What other properties of light can be stored in matter and recovered? And if we can build a chain of condensates, each one receiving a matter wave and converting it back to light for the next, what is the maximum distance over which quantum information can be faithfully transmitted? I don't know the answer yet. My lab is working on it. The piece of glass on your desk, the screen you're looking at, the fiber carrying the signal, they're all participating in the same physics in a small and imprecise way. That's not a metaphor. That's the mechanism. The universe has been building quantum memories out of ordinary matter since long before I arrived to describe it. I just made the first one that worked on purpose. Every message you'll send in your lifetime travels as light. Every secure communication, every encrypted call, every quantum encrypted transaction in the network being built right now depends on what happens when a photon meets an atom, on whether the information survives, on whether the medium can hold it and release it intact. Glass can hold it for a nanosecond. My condensate can hold it for a second, a minute, as long as coherence survives. The next generation of quantum repeater nodes will hold it long enough to pass it across a continent. The speed of light in glass is not a constraint. It's a clue. It's matter telling you that it can interact with light coherently, that it can slow it, hold it, process it. The glass has been doing quantum information science since before anyone had words for it. What I did in 1999 was listen to what the glass was saying and then take it to its logical extreme. The last thing I want you to sit with when this is over, you already knew that light slows in glass. You've known it since you were a child, but now you know something else. When light slows in glass, it is not losing information. It is entrusting it to matter. The atoms hold it, pass it forward, and release it, and the information arrives intact. That is not just a fact about glass. That is a fact about the relationship between light and matter at the most fundamental level. They are not different things, carrying information in different ways. They are two states of the same conversation. A photon enters glass and becomes briefly an excitation in an electron cloud, an atom. The electron falls back and the excitation becomes a photon again. In my condensate, I extended that moment, stretched the brief to a full stop long enough to control it. In 2007, I picked it up and moved it to a second condensate. The conversation between light and matter that happens in every window, every lens, every fiber optic cable in the world, I made it deliberate. I made it steerable. I made it a tool. And the question sitting underneath everything I've told you, the question that's not answered by any of this, the question I think about every morning when I walk into my lab at Harvard is simply this: what else can matter remember?